For this lesson, we're going to be taking a look at what are known as parent functions. A parent function is something that we should already have some familiarity with because we should be familiar with this idea of a quadratic function. You have studied parabolas quite a bit by now, both in reviewing for this course and your content from the previous course. A parent function is the simplest unmodified version of a function. So in the case of a quadratic relation, which is a function, the simplest version of that is just x squared. In the past, we would have written that as the equation y equals x squared, but now we are using function notation, and so I've written it as f of x is equal to x squared. Now, unmodified, well, I just wanted to give you an example of what a modified version might look like. In this case, I have the modified version in vertex form, and you're going to find quite a bit of similarity. A lot of what we talk about going forward from here is going to look very much like this vertex form. So let's take a look. Now, you may not be familiar with the radical function or maybe what the graph looks like, but the square root operator should be familiar to you. So the parent function for the radical function is just the square root of x. And I also wanted to get you used to the idea that although we typically will refer to f of x, there's nothing special or magical about it. That is a function of x, but we can label those however we want. So you can see in this case I decided to call this child g of x, whereas for the radical function, all the parents I named f of x. That was also arbitrary. But here the child of the radical function, you can see it bears some similarities to what we've talked about with respect to vertex form. It's not vertex form. This is not a parabola, so it would not be correct to call this vertex form. But some of the transformations that are in the transformation of a parabola, we're going to find those transformations cropping up again and again, and the same, or at least not the same, but similar notation. Another function that this one may be even newer to you than the radical function, is the reciprocal function. So it just means we take 1 over whatever we're considering. So the simplest thing to consider would just be x, so the reciprocal function 1 over x. And so here I've got an example of a parent. Doesn't look quite the same as those other two, but again, those ideas are still there. We'll talk about them in the future. And then the absolute value function, which again may be new to you. It's denoted by these two vertical bars. The absolute, you would say this is f of x is equal to the absolute value of x. And then here is an example of a modified child of that function. Now there's an infinite number of variations on these child functions from the parent. I was just giving a single example of each. I'm not going to spend any time looking at the quadratic in any more detail. We've done that quite exhaustively, both in this course and previous courses. So let's go ahead and start taking a look at some of these other ones. So the first one is the radical function. Y is equal to the square root of x. Whenever you're dealing with something that's unfamiliar to you, probably the best place to start is always going to be a table of values. So in this case, I've already preloaded this table of values with some sample x values. So what are the y values that go along with that? Well, when x is equal to negative 4, then y is equal to the square root of negative 4. But the square root of negative 4 does not exist. That's not a valid answer. Or another way sometimes we'll denote this would be inad, which stands for, that's the short form for inadmissible. You're not allowed to take the square root of negative 4. I like to refer to it as does not exist. It's not a real number. The square root of negative 1 does not exist. The square root of 0, well, that works. That's just equal to 0. The square root of 1 is equal to 1. The square root of 4 is equal to 2. And the square root of 9 is equal to 3. So let's see what will fit on here. I think this will fit fine. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's my value 9, there's 1, 2, 3, there's 4. And then vertically 1, 2, 3, 4, 5. So we have the point 0, 0. We have the point x equals 1, y equals 1. So that's the point 1, 1. We have the point 4, 2. So 4 and then up 2. And 9, 3. 9 and up 1, 2, 3. And if we do our best to draw a smooth curve for this, we end up with something like that. And if you look at this from the side, this actually looks like the side of a parabola. If you were to imagine looking at it as if this was the bottom of the graph. And that's not a surprise. A parabola is made up of x squared. This is made up of the square root of x. And squaring something and taking the square root of something, there's a relationship there, which we will be exploring in a later lesson. Now, let's take a look at this in terms of domain, range, a maximum, minimum, and maybe something that might be new to some people is the idea of asymptotes. Although I said asymptotes here, that's not correct spelling, it's asymptotes. So, the domain on this, what are the possible x values? And I want to bring you back to our table of values. We're not allowed to use this x value. We're not allowed to use this x value, but we are allowed to use these x values. And that informs us as to what our domain looks like. There's two ways to write a domain and range. We can write it in terms of where we're allowed to be or where we're not allowed to be. In this case, I'm going to write it in terms of where we are allowed to be. So I'm going to say that x is a real number such that, and now where are we allowed to be? We are allowed to be at x values that are greater than or equal to 0. They can be equal to 0. The square root of 0 is valid. Now what about the range? Those are y values, which are also real numbers, such that they have to be positive, same way that x had to be positive. So that's going to be y greater than or equal to 0. Does this have a maximum or a minimum? It turns out that this has a minimum. It doesn't have a maximum because this part of the graph, the y values just keep going up and up and up. And that's something else to point out. When we talk about a max or a minimum, we're talking about y values. So a maximum or a minimum means that is there a maximum or minimum y value? And in this case, we have a minimum at y equals 0. And an asymptote, I almost regret including this here because this one does not have an asymptote. And I haven't really talked about what that means yet. So I'm just going to leave that for now. I'm going to be talking about asymptotes as we go forward. Here's a nicer computer-generated version of the same graph. And as I had my domain and range, always positive for this graph, at least for the parent function. This domain and this range won't always be positive depending on the parent function. We'll talk about that going forward in the course. All right, let's look at another parent function. We're going to look at the reciprocal function. So the x value, we're going to start with a table of values. When x equals -2, then my y value is going to be 1 over -2. And I don't like negatives in the denominator, so that's just the same as -1/2. When y is equal to -1, or sorry, when x is equal to -1, the y value is 1 over -1, and that's just -1. When x is equal to -0.5, that's 1 over -0.5, which is actually equal to -2. When x is equal to 0, I have 1 over 0, and that does not exist. That's not an acceptable value here. So we have no answer. And actually, you know what? I don't want to use does not exist here. I want to use undefined. It's a little bit different than does not exist and it's something we can discuss in class. If you're curious, you can go look up what the distinction would be between those. But the bottom line is there's no answer here. And then 1 over 0.5 is equal to positive 2. 1 over 1 is equal to 1. And 1 over 2 is just 1/2, so we leave that alone. So let's go ahead and put a scale on here. 1, 2, 3, 4. So this just goes out to 5. 1, 2, 3, 4, out to 5. -1, -2, 3, 4, out to -5. And -1, -2, -3, -4, and -5. When x equals -2, y is equal to -1/2. When x equals -2, y is equal to -1/2. When x equals -1, y is -1. And when x equals -1/2, y is equal to -2. When we can't do anything about when x equals 0. So there's something that's very special about x equals 0. When x equals 0.5, y is equal to 2. Then when x equals 1, y is equal to 1. And when x is equal to 2, y is equal to 1/2. Now, the way we deal with x equals 0 being off limits is by introducing what's known as an asymptote. This is, in fact, what's known as a vertical asymptote. So this is a vertical asymptote which occurs when x equals 0. An asymptote is a line that your curve will approach but never touch. And that informs us a bit about what the shape of this thing is going to be. Now, there's something else I want to consider, and I need a little bit more room for it, which is, let's go back to the expression y equals 1 over x. If I multiply both sides by x and divide both sides by y, or another way of thinking of this is cross-multiplying, I can turn this expression into x equals 1 over y. And you can see when I do that, 1 over y, well, this means that y is not allowed to be equal to 0. This one, where x is in the denominator, means that x is not allowed to be equal to 0. And if I just rearrange this very simply, I get y is not allowed to be 0. And so that is known as a restriction, and that actually applies here as well, and it actually results in another asymptote. This one is known as a horizontal asymptote, which I usually write as HA, and this is a horizontal asymptote at y equals 0. And once again, I'm missing t's. I bet I'm missing t's in all of them because I copy and pasted. I'll fix that in the class note. So we've got a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. I'm going to talk more about what asymptotes mean, but for now, it is the simplest discussion of this is going to be we're not going to cross these, we're going to approach them but not cross them. So this side of the graph looks like this, and over here I get that. And so that's what this graph ends up looking like. This is the graph of the reciprocal function. And now we can put together a little bit of info here. As far as the domain goes, the x values, so you can see when I put in x equals 1/2, I had a y value. When x equals 1, 2, and as I continue along in the positive x direction, I am going to get y values. If I go in the negative x direction, I'm going to get y values. So it turns out that most x values are actually permitted here. So it's x real values. And this is one of those cases where it might be better to actually talk about where x is not allowed to be, because the only place it's not allowed to be is at 0. So this is one where we write the domain in terms of where it's not allowed to be. I sometimes talk about domains in terms of positive and negative, meaning positive saying you can be here and negative saying you cannot be there. The y for the range is going to be very similar. It can be all of these values up here. It can be all of these values down here. The only place that we don't have a y value is at 0. So we say y is not equal to 0. Do we have a maximum or a minimum? We do not. There is no, this y value continues up towards infinity. This y value continues down towards negative infinity. So we have no maximum or minimum. And then the asymptotes, with a t, the asymptotes are, as I've already said there, we have a vertical asymptote, and that occurs at x equals 0. And we have a horizontal asymptote, and that occurs at y equals 0. And these asymptotes, these are equations of straight lines, so they must be written in this form. And here is a nicer computer-generated version of the same graph, but it shows all the same things. Okay, now let's wrap up our graphs, at least, with looking at the absolute value function. So the absolute value function basically just gets rid of negatives. That's what its job is. So if you give it a negative value, it gives you a positive value. If you give it a positive value, it just leaves it alone. So in this case, the absolute value of negative 3 just turns into positive 3. The absolute value of negative 2 turns into 2. The absolute value of negative 1 turns into 1. The absolute value of 0 is 0. The absolute value of 1 is equal to 1. Let's make that more obviously a 1. The absolute value of 2 is equal to 2, and the absolute value of 3 is equal to 3. It's really not a very interesting function when you write it out this way, but it does end up having some interesting properties and actually some fairly important mathematical properties. So once again, I'm going to number out my scale. Every 2 blocks is 1. Now you might start to think, okay, well, absolute value, not allowed to be negative, so does that mean I'm going to end up something the same as what I did with the radical? But no, not quite, because in this case, we're allowed to put negative values in. We just don't get negative values out. So if we start from negative 3, which is here, at negative 3, I actually got a value of positive 3, which is up here. At negative 2, I got positive 2. Negative 1, I got positive 1. At 0, I had 0. Then at 1, I have 1. At 2, I have 2. At 3, I have 3. And you might think, well, oh, it's like a parabola. And I guess there's a very loose connection to it being a parabola or looking like a parabola. But what it actually ends up looking like is this. So you end up with this V shape. So yeah, I guess it's like a parabola in the sense that it's going to either open up or open down depending on the a value in front. The parent function opens up, but the difference is no curves. It's just this straight line or 2 straight lines that meet at this single point. Now, what about the domain of this? The domain of this one is x member of the reals. It's all, you can put any value of x in here and it will turn it into the positive version. So for the parent function, that means the y values are always going to be positive. Does this one have a maximum or a minimum? Yes, it has a minimum at y equals 0. And once again, a misspelled asymptote. Does it have any asymptotes? No, it does not. And once again, a nicer computer-generated version of this. For my classes, where I'll be seeing you in person, all of these graphs are going to be given to you, and you're going to graph them in terms of, I've got a handout for you to work through this stuff. Okay, so now just some stuff that I'm going to want you to capture in your notes. I've already talked about most of this stuff, so this is really just going through the putting into text what I already put into words. So first of all, the idea of asymptote. Glad to see that I'm finally spelling it correctly here. So an asymptote is a straight line. Actually, it doesn't have to be a straight line, but most of what we deal with is going to be straight lines. So it is a line that a curve approaches but never touches. So we took a look at the reciprocal function. That was this one. And as we saw, the reciprocal function itself had two asymptotes. It had a vertical asymptote and it had a horizontal asymptote. These are the equations of those asymptotes. They're straight lines. Notice that the equations are equal signs, but the domain and range use these same x equals 0, x, y, and y equals 0, except for the domain and range specify where you're not allowed to be. So these equations say where the lines are, and the domain and range specify you're not allowed to put any x or y values along there. The absolute value function, another way that you talk about absolute value is it is interested in the size of a value. It is not interested in the sign. So how large is that value? It doesn't care whether it's a large positive number or a large negative number. It's really just measuring the size of the number. Another word you might hear in association with absolute value is magnitude. And the representation, as I pointed out on the first page, is these vertical bars. Now I say the result will always be positive, but there is a caveat that goes along with that, which is once we get into more complicated versions of these, there are some manipulations that you may do to this. The absolute value function itself will always be positive, but we can create expressions that involve the absolute value function that could still have a negative result. And there's more to be seen on that later on. Okay, and that's it. Nothing from the textbook for today. I have some worksheets. I'll put those on the web page and hand those out in class.